Hello everyone, welcome to EnviroPioneers. In this video, we will understand the concept of Universal Transverse Mercator projection. As we learned in the last video, that the shape of our Earth, it is not perfect sphere, it is in the form of the ellipsoid and also the surface is uneven. So to define the location of real world feature on the 3D Earth, we need the use of the geographic coordinate system. In geographic coordinate system, we include the use of the datum, which is the combination of the geoid and the ellipsoid model, which are two framework for calculating the latitude and the longitude as well as the elevation. So by using the geoid and geocentric ellipsoid, we create the geodetic datum which best fit for entire Earth, and this is suitable for calculation of the latitude and longitude of any location as well as elevation with respect to the geoid. And the projected coordinate system is used to define the location of the real world feature on two-dimensional framework. It can be either the piece of paper or it can be the computer system on which we are working. So here we can see that this is the GCS and here we are having the PCS. So GCS, that is the geographic coordinate system, it defines the location of the any place or any object on the three-dimensional Earth, and it is mainly given in terms of the latitude and longitude, while with the help of the mathematical algorithm the same information is converted into two-dimensional framework in the projected coordinate system, that is the PCS, and here the location is given in terms of the meter. As on the three-dimensional Earth, we have the graticule of latitude and longitude where the location is defined in terms of the latitude towards the north and towards south, and the longitude in terms of the east and the west. So this information of 3D Earth, it is transferred onto plane rectangular coordinate system where the location is defined in terms of the positive x and the negative x and positive y and the negative y with the help of the mathematical calculations. So there are many different type of projections depending upon which particular property we want to preserve during the transfer of information on the two-dimensional framework. For example, here we have some of the famous projections and their type, key virtues and the uses of them. So stereographic projection, it is mainly the azimuthal projection which preserve the shape of the features, and it is mainly used in the areas over the pole or for the small scale continental mapping. Then we have the Lambert conformal conic projection which also preserve the shape, and it is mainly used in the mid latitudes, example USA, Europe and Australia. Then we have the Mercator projection which is cylindrical projection, and it is also conformal and the true direction, and it is mainly used in the areas around the equator and for the marine navigation. Then we have the Robinson, that is the pseudo cylindrical projection, and here all the attributes are distorted to create a more pleasant appearance, and it is mainly used in the areas around the equator. Then we have the transverse Mercator projection which is also preserving the shape, and it is used for the areas with the north and south orientations. Now coming to the Universal Transverse Mercator projection system. So this projection is based on the Transverse Mercator projection which was invented by the John Henrik Lambert. Lambert modified the Mercator projection by changing the aspect of the developable surface to transverse. So in the normal Mercator projection, here the developable surface, it touched the equator, but by changing the aspect to transverse, the developable surface touch the earth or the globe along a particular meridian. In this image, the red line, it represents the central meridian, and the size of the circle, it represents the amount of distortion. So we can see that along the central meridian we are having the homogeneous circles, but as we move away from the central meridian, the size of the circle, it increases, representing the increase in the amount of distortion. But the distances are true along the central meridian where the developable surface touches the surface of the earth, and all the distances, directions, shape and area, they are reasonably accurate within the 15 degree of the central meridian. But here the problem is that all the meridians and the parallel, they are no longer a straight line as it was in the case of the regular Mercator projection. So, in order to minimize the distortion, several modifications were made, which is now referred as the UTM projection. And the National Imagery and the Mapping Agency, which was formerly the Defense Mapping Agency, they adopted a spatial grid for military use throughout the world, which is referred as the Universal Transverse Mercator grid. So here we have the different zones. Now let us see how this Universal Transverse Mercator projection is different from the regular Transverse Mercator projection. So first thing is, here the globe is divided into 60 zones, and how it is done? So here we can see that this is the developable surface which is kept in the transverse aspect to the globe, and the developable surface it touch along a particular meridian. So this is the central meridian. But when we rotate this cylinder by 6 degree, now this developable surface will be touching some other meridian. So this universal transverse Mercator projection, it is applied repeatedly by using the multiple cylinders that touch the globe at 6-degree interval. As there are total 360 longitude lines, so when we rotate these cylinders by 6-degree interval, we get total 60 projection zones, and each of the UTM zones, they have their unique central meridians. These UTM zones are numbered 1 to 60. The number 1, it starts at the anti-meridian, which is also the international dateline, and the numbering it proceeds towards the east, and the zone 1 it extends from 180-degree west to 174-degree west, and so on. The second point in the UTM projection is to avoid the extreme distortion that occur in the polar areas. The zones are limited to 84-degree north and 80-degree south, and this is done by using the secant cylinder that cuts the globe at the 84-degree north latitude and 80-degree south latitude. So each of the UTM zone is having the width of 6-degree longitude, and they extend from the 84-degree north to 80 degrees south. And in the polar regions, the universal polar stereographic grid system is used. When we use the transverse aspect in the tangent cylinder, we get one central meridian. But when we use the secant cylinder, we get two standard meridians. So the third consideration is with respect to the selection of these two standard meridians. So to improve the overall accuracy of the measurement, this cylinder is made to intersect the globe at two standard meridians that are 180 km east and 180 km west of the central meridian. And this result in true scale along the two standard meridian of the longitude. So the standard meridians, they have the scale factor of 1. It means the distance of 100 meter in the ellipsoid would be the same as on the map projection. And the center line of the UTM grid, it has a scale factor of 0.9996. It means the distance of 100 meter on an ellipsoid would be 99.96 meter on the map. So to compensate for the scale distortion that is introduced along the central meridian, a scale factor is applied to all the distance measurements. By using the transverse secant cylinder, we get the UTM projection zones, and each of them are of 6-degree longitude width and extending from 84-degree north to 80-degree south. And the UTM coordinate system, it is formed by superimposing a regular square grid on each UTM projection zone of 6-degree longitude width, and the grid is aligned so that the vertical lines are parallel to the central meridians. By doing so, we have the projection of the entire globe extending from 80 degrees south to 84 degree north on two-dimensional framework in total of the 60 zones. The first zone extends from 180 degree west to 174 degree west, and it continues towards the east, and the last zone is from 174 degree east to 180 degree west. And each UTM zone is divided into horizontal bands at the interval of 8-degree latitudes, and these bands are identified by the letters which extend from south to north, beginning at 80 degrees south with the letter C and ending with the letter X at the 84-degree north. And the letter I and O are skipped to avoid the confusion with the 1 and 0. And the last band, which is the X band, this is the only band which is having the interval of 12-degree latitude. But rest other bands are having the interval of 8-degree latitudes. One thing which is very important to keep in mind that N band is the very first band after equator towards the north. So suppose if we face the difficulty in remembering the alphabets, so we can keep this point in mind that N, it represent the starting of the northern area. So any letters which is falling after N, that represents the northern part, while any letters before N, it represent the southern hemisphere. So the UTM system, it divides the earth into 60 zones, each of them of width of 6-degree longitude, and each zone defines the reference point for UTM grid coordinates within the zone. And the UTM grid coordinates are expressed as a distance in meter to the east. This is referred as the easting, and distance in meters to the north, and it is referred as the northing. So for a zone, x-axis is the equator, y-axis is the central meridian, and the intersection point is referred as the origin. And as xy are used to denote any point in the plane rectangular coordinate system. So here in this case, easting and northing are used in the UTM coordinate system. So let us see what is this easting and northing. Easting are used to determine the east and west position with respect to the central meridian. And this central meridian is assigned an easting value of 500,000 meter east, which is arbitrarily assigned, and all the points which are lying towards the east will have the easting value more than 500,000 meter east, and the points which are lying towards the west will have the lower values in comparison to the central meridians. By using this arbitrary value, an easting of 0 it never occurs, since a 6-degree wide zone it will never be more than 674,000 meters wide, because at equator the distance of 1 degree longitude width is approximately 111 kilometer. So 6-degree longitude width will be equal to approximately 6 into 111 kilometers. So that will be always less than this. So the minimum and the maximum easting values at the equator is 160,000 meter east to 834,000 meter east at the equator, while at the 84-degree north it is ranging from 465,000 meter east to 515,000 meter east. Now coming to the northing, so the UTM northing coordinates, these are measured relative to the equator, and for the locations which are north of the equator is assigned the northing value of 0 meter north. So we can see here as we move towards the 84-degree north, we can see the increase in the values. So 0 kilometer, 2000 kilometer, 4000 kilometer. So we can just multiply by 1000 to get the values into the meter. To avoid the negative number in the northing values, the locations which are south of the equator, they are made with the equator assigned a value of 10 million meters north. So we can see here that for the southern hemisphere, the equator is assigned the value of 10,000 kilometer, and as we move towards the south pole, this value it decreases 8,000, 6,000, 4,000, 2,000, and in the northern hemisphere, the northing values it stretch from 0 meter at the equator to 9,350,000 meter at the 84-degree north. While in the southern hemisphere, the northing values it range from 10 million at the equator to approximately 1,100,000 meter at the 80-degree south. So in the northing, we are having the two reference values. For the northern hemisphere, the value of the equator, it is starting from the 0 meter, while for the southern hemisphere, the value of equator, it is starting from the 10 million meter. In the UTM projection system, easting and northing, they are often referred as the false easting and false northing because the values are based on the arbitrary value assigned to the central meridian and the equator. And some UTM northing values, they are valid for both north and south of the equator. So in order to avoid the confusion, the full coordinate, it should be specifying whether the location is north or south of the equator. And usually this is done by including the letter for the latitude band. So here we can see this is for a particular place. So the location is also mentioned in the latitude and longitude, and also we have the coordinate in the UTM projection system. So here are the values starting from 35T and some values in meter east and meter north. So 35 is the UTM projection zone and T is for the latitude band, and as it is falling after N, it means it is in the northern hemisphere, and this meter east, it refers for the longitude and this is for the latitude. In UTM projection system, the accurate information about the location, it can be obtained by dividing the grid squares into further subdivisions. As we can see here, this is the 1000 meter square which is undivided, but it can be divided into 100 meter squares. And each 100 meter square, it can be divided into 100 10 meter squares, and each 10 meter square, it can be further divided into 100 1 meter squares. And like this, the accurate information of any location, it can be obtained. If you have understood the concept, you can also check it on the Google Earth. So when we open the Google Earth, we get the latitude and the longitude in the decimal degree. But here we have this option when we go on the tools. So here we have this options. So we can change into any other projection system. So for example, here we have the Universal Transverse Mercator projections. I am selecting this, apply and OK. So here when we move the cursor, the latitude and longitude you will be getting in the UTM projection, but because as the letters are very small, it will not be visible to you. So I'm just taking a place mark. Okay, so you can see that as I have selected a particular place mark, here I get the zone, that is 43R, and then we are getting the easting and the northing value. So if I move this particular place mark, you can see the change in the zone as well, and also the easting and the northing value. So I have placed it somewhere here. So we are getting the 45P and then also change in the easting and the northing value. So let us see whether there is change in the northing value after N or not, because N is the latitude band which is starting after the equator. So after equator there should be increase in the northing value. So let us check that. So I am moving the cursor, so you can see that there is decrease in the northing value, and as we cross the N. So now at this particular place here we are having the 44M, and you can see that there is sudden increase in the value of the northing, and here it is now mentioned as the meter south. So when we move the cursor up and down, there is change in the latitude within a particular zone, but as we move the cursor left and right, there is change in the zone number. So with the change in the UTM zone, there will be change in the easting values. So within a particular zone, the numbers will first increase, and then as the zone change, again we'll be having the start of the easting values from a lower to higher number. So you can explore the same by moving the cursor or by placing the place marks at different location, and you will see the changes in the zone as well as the easting and the northing values. And as we move the cursor, the zone is also changing as well as the alphabet, that is the representation of the different latitude bands, that is also changing. So you can just explore the same for understanding the concept of the UTM projection system. These are some of the references from where the content of this video have been taken. I will suggest you to go through this particular PDF. The link of this is also mentioned in the description box. Thank you for your continuous support. We will meet soon in the next video. Thank you.